Hello, Dan. Nice to connect. And thanks for.
Morning, folks.
Professor. Hi. How are you?
Pretty good. And yourself?
Yes, fine. So, Professor Reason, how are you? Reason, sir, are you here? So, Duncan, how is going on your research work? How is going on? I think right now you are in your university, right?
That's right. Yeah. Yeah, it's going good. I'm in a brand new office, so I don't have any display in the background, unfortunately. I need to put some nice pictures up of the mountains and so on. But yeah, it's all good. Thank you.
Okay.
I have a nice painting from one of my students, which is going to go in the background there. Oh, upside down.
Oh, that's so nice. That's so nice.
Yeah, pretty good, eh?
Yeah, really. It's really good. So I think so sharply at 2 p.m. we will start, and Regan sir I think has joined. Professor Regan, are you here? Okay, just to left. Okay, let him join. Then we will start. So we are also proceed regarding our discussions, Duncan, of the Himalayan Climate Dialogue and Climate Consortium part. So hopefully very soon we will have a discussion with you and Rizal and other officials, those who are in, right now is joining one by one. So we will have a discussion and how that kind of international collaborative activities we may plan accordingly. So that I will discuss.
Yeah, sounds
And
good.
I will let you.
Thanks, really good.
Yeah, and also we are planning to. I request you to send one article, particularly on your research work on Himalayan case studies basis, as that we in our coming SAIARD Chronicles we would like to publish is through online, through LinkedIn newsletter or article format. So we were, and already it has a more than 1,000 subscribers, 1,100 subscribers. So I think you please share one article for our next October session.
Yeah. You just send me the details. Tell me what I need to do, and as long as it doesn't take too long, then time is of the essence these days, unfortunately.
No, I will share. Don't worry. And okay. So let Region has joined. Then we will start. I think what happened. Antara Region has joined. Professor Region. Just call him. Otherwise, we may start with Professor Duncan. Then let Region has joined. Okay. Please call him. Duncan, just a second. Let him join. Otherwise, we will start with your lecture.
Yeah. Good afternoon, everyone. Hello, Duncan. I just got a phone from Rizan sir. So I would like to convey a message on his behalf.
Okay.
He is waiting for his connection to be restored. Unfortunately, he got disconnected. If it takes much more time, Professor Duncan to with his presentation, but I think we wait for a couple of minutes And if he doesn't join in a couple of minutes, he requests Professor Duncan to go ahead. So thank you.
Okay. So I think Professor Duncan may start, and let him start, and then after that, Rizan sir can join in between, no issue. And after Duncan, we will go for his presentation. Duncan, is it okay?
Yeah, that's absolutely fine. I don't mind either way.
Yes, sir. That's what.
Okay.
Go ahead, yes.
So I think Andhra, you please start. Yeah. Then Professor Rizan would let Rizan sir as join. I think until that time we may start with Professor Duncan.
Okay.
Screen share off করো।
Good afternoon, everyone, and welcome to today's important session on GLOF risks and resilience, strategies for a changing climate. I am Amrita Datta, Research Associate in SAIARD, and it's my pleasure to serve as the moderator for the timely and critical discussion. As we witness the accelerating impacts of climate change, one of the most alarming threats in mountainous regions is the growing risk of glacial lake outburst floods or GLOFs. These sudden and often devastating events occur when rising temperatures cause glaciers to melt rapidly, creating lakes that can breach their natural barriers and unleash torrents of water downstream. The consequences of such floods can be catastrophic, destroying communities, infrastructure, and ecosystems in a matter of hours. Today, we are not only here to understand the science behind GLOFs, but also to discuss the urgent need for resilience building strategies. How can we better predict and prepare for these floods? What policies, frameworks can help mitigate their impacts? And most importantly, how can we support the vulnerable communities that are on the front line of these disasters? To help us explore these questions, we are joined by two outstanding speakers who each bring a unique perspective from cutting-edge scientific research to on-the-ground experience in community resilience. Together, we will delve into the latest innovations, strategies, and collaborative efforts that are shaping our response to the growing threats with a focus on practical solutions for adaptation and preparedness. Without any further delay, let's begin the session with our first speaker, Professor Duncan Quincy, a professor of glaciology from School of Geography, University of Leeds. Over to you, sir.
Thanks a lot, Amrita, for the opening remarks. Very good. Very concise summary of the challenges. So, can you just confirm, Amrita, that you can see that slide?
I think it is coming.
Yes, sir. Yes, sir. It is seen.
Okay.
It's good? Okay. So, I mean, first of all, thanks very much for the opportunity to join today and to speak to you. Thanks, Biswajit, for all of the efforts that you've been putting in over the last weeks to establish this, connection and for us to be able to work together. And I'd just like to give a few thoughts really on some of the outstanding challenges for glacial lake outburst flood assessments. Using some of the recent research that we've been doing where we're coming up against some major uncertainties in what we're trying to do. And I'll just present a few ways forward that I think we can make some progress to better address what the risks may be. And hopefully that'll feed into the discussion then around how we increase resilience to these sorts of events. So, well, as you now know, my name is Duncan Quincy. I'm a professor of glaciology here in the School of Geography at the University of Leeds. And I've been working in the Himalaya for quite a long time now. I actually started looking at glacial lake outburst floods with my PhD, which was probably about 20 years ago. Hard to believe, but that's how it is. I moved away a little bit from the hazards after that and looked at ice dynamics and how these glaciers are evolving with climate. And I must admit, most of my recent work is about future projections of glacier evolution. But some of my PhD students have brought me back to looking at glacial lake outburst floods. It's clearly of such major importance for this region that we're really starting to address this head on again and try to make some steps forward. So I just give you a little bit of a summary as to some of the things that we've been up to and the sorts of things that I think we need to make progress with going forwards. I feel like a little bit like probably many of the people on this webinar know as much about glacial lakes and their formation as I do. Many of the people I see are actually from the region where these glacial lakes are forming, and I'm very conscious that I'm coming at this from afar. But to give some basic background, I think probably most of you are aware of the increasing emergence of these glacial lakes within high mountain regions of the world, particularly so in the central and eastern parts of the Himalaya, where the glaciers have been so heavily in recession for the last, well, 3, 4, 5 decades, and where the ice used to sit, that ice has now melted back, and in many cases where the meltwater is trapped, we get the development of these lakes, which in the case here of Shorolpa, for example, can be several kilometers long. And the amount of water that can be stored within these lakes can be some millions of cubic meters. And as the introductory remarks said, the sudden release of this water downstream can have absolutely devastating effects for the channel, for the people, for the lives and livelihoods of those who live in those downstream areas. And so it's of quite some concern that we see the sorts of studies that came out from Dan Sugar a few years ago, where we can observe global glacier lake volume increasing quite systematically year after year after year. And it's true to say that the lakes in high mountain Asia in particular, if we're to focus in on those on the map, you can see that the absolute volumes that are stored within these lakes at the moment are perhaps smaller than in other parts of the world. But their increase in size is relatively quite fast, actually. And in the particular case of high mountain Asia, of course, these downstream areas are quite heavily used, in some cases heavily populated. And so the connection there between these glacial lakes which are developing and actually the people who are living within these environments is very direct. And perhaps you can't say that for necessarily for other parts of the world. So although the lakes themselves may be smaller, they're certainly suspended at high elevation. And the people who are making use of the land and who are living in those areas in the downstream are particularly concentrated. And so therefore, the lake development is of particular concern in this area, I would suggest. I think this has been highlighted very, very starkly within the last couple of years, even within the last few weeks. Many of you will be familiar with the lake outburst event that swept away Tame village in the Everest region of Nepal. This was particularly devastating for this area, highly unpredictable in this particular case, but really emphasizes some of the challenges that we're seeing with trying to prepare for and mitigate against these sorts of hazards. And again, many of the people on this call will be familiar already with the outburst from South Lonak Glacial Lake back in 2023, and the devastating effects that that had on the downstream areas, taking away buildings and highways, and impacting many of the villages within the valley. So some very stark examples of how current this sort of challenge is. And I think as a community, we've done quite a bit to be able to start to look in a systematic way at how we evaluate what these hazards look like. We can start to quantify really how major that hazard is. And it's quite nicely laid out, if you're not familiar already with it, in the white paper, the technical guidance document that's there on the right-hand side that you can download from the GAPHAS website, where you can go through each of the different parameters that affect how dangerous a lake may or may not be, and start to put some numbers on it and start to quantify some relative hazards across an area. So we've made some good progress, as I say, but I think there's probably quite a few areas where we still have some challenges, and I'll just go through these one by one. These are the main ones in my mind, but there's many more, and I just thought I would bring these ones together with the thoughts that I think these are areas which we could make some good progress quite quickly. The first is that these existing hazard assessment protocols generally don't or can't take account of the moraine dam stability, which seems to me a bit of a funny thing, really, in that the dam is the major thing which is holding these lakes back, yet it's probably the thing that we know the least about. So I think well, I can give a few examples, but I think we can make some quantitative progress in this quite quickly. The second thing that I will talk about is that future lake locations remain highly uncertain. So if we're thinking about where these lakes will develop, then that's actually not quite as straightforward as what you might think. There's quite a lot of uncertainties in those models, and it makes it difficult to plan and to ultimately mitigate against future disasters. And then the third area that I'll just touch on very briefly is about the downstream areas and how we can, or the challenges we face in being able to predict how the lake outburst floods will evolve once they're released, particularly then in a cascading sense, when one event can lead to a whole host of other processes. So we'll just think briefly about some of the knowledge gaps that remain in that particular area. Just to start then with the first of those, and to think about that dam stability issue. As I say, this is something which I think we probably need to make some progress with quite quickly, because as you can see here, the Tulagi Moraine Dam, which I know that Professor Rijan has been working on himself, it's a good example of one of these areas that is holding back, a lake which is now over 1 kilometre squared in size. You can see the satellite image in the bottom right there from Sunri's publication in 2020. This is a lake that grew quite rapidly through the 1990s, and now sits at the head of a valley. It's around 4,050 meters in elevation, and the downstream area is not immediately well populated. There's some farming activities in those downstream areas, and there's some villages a little bit further down, but certainly quite a lot of vulnerability in the area below. So this is one of these dams which it would be quite critical, really, to understand how stable it is within a warming climate. We do know from some previous work that it's ice cored, and we do have some basic information about its length and its width. And with the recent digital elevation data that we can get hold of now, the 8-meter data, we can actually start to plot the topographic profiles, which we need for a bit more of a quantitative assessment of how stable this dam is. So this is something that we've been trying to just get a bit of a better handle of, and looking at dam stability is something that geotechnical engineers do quite routinely. I have to say I'm not a geotechnical engineer, but fortunately I have some contacts who are, and we can start to put some numbers on whether these dams are stable or not. And so this slide is a little bit intense, and so are the next couple, but they're largely showing, if you'll just bear with me, on this particular plot, a cross-section through that moraine dam that we saw at Tulagi. So on the left-hand side, you've got the lake. You can see that in the blue with the blue arrows pointing down. They're the forces which are pointing down. You can see the topographic profile through the dam crest. That's in the middle of the plot. And then the downstream area as it goes off down towards the right-hand side, where it's talking about the toe. And the distance is plotted along the x-axis, so you can get an idea of the scale here, and the elevation is on the y-axis. And so using software such as SlopeW in this case, I think we can start to say something about the inherent stability or instability of these dams if we make some assumptions about the material properties. And so you can see some of those factors that we put into this sort of model at the top there, the cohesiveness, the angle, the friction angle, and so on and so forth. And with this sort of analysis, then we can start to plot what the failure planes within this dam structure might be under various forcings. And so at the moment, this is looking at a steady state scenario. It doesn't account for any avalanches into the lake with overtopping or anything like this, which is probably the next step for it. But in the first instance, looking at some of those basic parameters and feeding them into the model, we can see with a steady state scenario, so there's no forcings here, there's no earthquake, there's no overtopping, nothing like this, just as it is at the moment. The factors of safety, which you can see there in the table, the factors of safety that are in the colors, they're all well above the value of 1. And we would take the value of 1 normally to indicate, well, this is a time where we're a bit worried. If it's a factor of safety above 1, we can say that it's fairly stable. If it's a factor of safety below 1, then this is a time, or this is a scenario where we would expect to see some failures within the dam structure itself. So you can see that just under steady state conditions, this lake actually seems to be fairly well contained by this dam. The factors of safety are all well above 1. In fact, they're mostly above 2. We use different sensitivity tests to look at the impact of changing some of those assumed values of the material properties. But in all cases, we really can't get this dam to fail under just a steady state scenario, which is good news in this particular instance, of course. If we then start to think about if there were another major earthquake, well, would this particular dam be safe? Then we can apply to that existing model some ground acceleration, 0.25 g in this particular example, and just look then at whether this dam would still remain stable under that scenario. And you can see there that under that scenario of 0.25 g, the factor of safety is 1.089. That's just on the middle right-hand side of the slide. And there may be some shallow failures in the green there, but really not a lot that we would be concerned about in that particular circumstance. So again, some pretty good news really for the Tulagi scenario. If we then increase that acceleration up to a value of 0.5 g, then in the red, you can start to see where these failure planes might be expected to develop. And we can tune those values up, and we can look at what the factors of safety may be. And you can see that once you increase the gravitational acceleration beyond that initial value of 0.25, then we start to get some pretty big failure planes. And this is the point at which we could then become concerned about this dam, this particular dam failing. And if you increase the acceleration up to 0.5 g, which is approximately the same value as what was in the Gorka earthquake back in mid-2010s, then you can see the large failure plane that we might expect in that scenario. And that's something that then we'll be particularly concerned about. So I think this is something, it's a good start on something that we could take forward as being a form of analysis for looking at marine dam stability across a broader area. What we really need to be able to do to take this further is to get some more information on the actual marine conditions. This is now the Tulagi Dam looking at the other way, looking up the valley. And you can just see the glacier just round the corner in the long vision of the photograph. And I think we really need to get some more information on exactly what those material properties are like within the moraine dam, because at the moment we're really just testing them through sensitivity analysis, and we don't really have a good idea of what their absolute values are. And we could also do with having some more information on whether there's an ice core there, for example. This is pretty key in this sort of scenario. And with some basic digital elevation model differencing like we've got here, you can start to see in those red mottled areas within the middle of the image, those places where we do think that the ice core is degrading particularly quickly. So some areas for development there, I think, in terms of moraine dam stability. The second thing that I think we can make some progress on quite quickly is in modeling the future locations of glacial lakes. This is something which has really come about very quickly in the last 10 years. This ability to be able to take contemporary digital elevation model data and subtract from it ice thickness model data, and from that, using the hydrological tools, be able to fill in where the voids are and to be able to model where the overdeepenings beneath these glaciers are and where we might expect future lakes to form. And you can see there an example from the Linsbauer paper on the right-hand side, where you've got in A and D, you've got the contemporary digital elevation model, and that just shows where the glacier is and what its current surface is. Then you subtract the ice thickness, you can see the subglacial topography in B and E, and then you can fill in where those holes are, and you can see in C and F where we might expect those future lakes to be. And these methods are given a really crucial window into the possible location of future lakes, and they've now been run even at global scales to identify these. Another good example from that paper here is if you roll it out to the broader area, you can start to see in some of those blue filled in zones where the overdeepenings are, not just where they are, but what their size is, what their depth is, what the volume of these overdeepenings are. And that gives us a really good clue as to where we might expect these lakes to emerge and start to think about, well, where are the biggest lakes going to be and who are they likely to impact? So this is fantastic, but what we've really not done yet as a community, I think, is drill down a little bit more into how reliable these data are and can we actually take them as being robust. And so we've been working here in Leeds a little bit on, if you take different digital elevation models and you take different ice thickness products, what sort of answers do you get? And do you get consistency? And what we found is that actually you don't. And that these outputs are really quite highly dependent on particularly the ice thickness model that you might use. And so there's a few ice thickness models around now. There's the Daniel Farinotti ensemble, there's GLABTOP 2, there's the Husson Farinotti output, there's the Milan et al. Output, and there's also OGGM, which you can do ice thickness with too. And what we find for a sample of glaciers within the Himalaya is that depending on the ice thickness product you use, you get very different outputs, very different results in terms of what their depth might be. You can see here on the violin plot that they can stretch all the way from overdeepenings which go down to 250 meters if you use OGGM in this particular case. And for example, the Husson Farinotti finds a maximum depth of 150 meters. So this is a little bit alarming, I suppose, when there's quite a lot of papers which are out there looking at future lake locations based on just a single analysis like this. And this, I should say, is the work of Ipsita Nayak, who's been working with me here in Leeds this last year. This translates through into great variability in terms of the number of overdeepenings within this subsample that we looked at. Again, you can see the different ice thickness product we used on the x-axis and the number of overdeepenings on the y-axis. Big variability. So really, is it okay to just take one of these models and just publish those results and say this is how it's going to be? I think we'll probably need to rethink this a little bit. And then again, this is Ipsita's work where she's rolled this out not just for the Himalaya, but looking at the European Alps, the Southern Alps of New Zealand, the Peruvian Andes and Alaska. And you can see that there's also a lot of spatial variability. So this depends on exactly which region you're looking at as well, as to whether there's consistency between the models or whether there's a lot of differences. So some work here, I think, to be done. I think some more of this sort of intercomparison work where maybe we start to look at the commonality between some of these models, and we find the areas where there's agreement between those models might give us a better idea of where these over-deepenings may be appearing as these glaciers recede. The third area then that I'll just touch on extremely briefly is how are outburst floods going to evolve when they when they cascade into the downstream areas. And knowing exactly what the lake expansion will look like and then the type and mode of failure, I think is really quite tricky to put some numbers on at the moment. So the numerical models are a little bit limited in terms of when you see these extreme floods cascading down into the valley, exactly what the parameters to be able to model them effectively might be. And I think there's a few areas where we need to collect a little bit more data to be able to say something more about this. In particular, knowing just how much water could be involved in the flood would be good to know. So can we make some more progress on establishing what the lake volume is? Can we do this by bathymetry? Or actually is volume area scaling effective across broad areas? And is it robust? How do we know exactly what the freeboard is? Can we measure this? Can we use digital elevation data to see how much this changes over the year? So if an outburst event happens at one time of the year, will it have a bigger magnitude in the downstream area than it does if it occurs at a different time of the year? Exactly how do we handle the displacement waves from the mass movement? Can we bring in models which are more tuned for tsunamis, for example? And again, going back to the dam stability, how do we know exactly whether the dam will fail completely or only partially? And can we get more information on the internal characteristics? Then once it's in the downstream area, how might we actually be able to model how it behaves and propagates? Can we use high resolution topographic data to drive the water flow in the models to make it a little bit more accurate? Or actually, are the course data that we use at the moment okay? And I think some experiments really to look at whether the resolution of the topographic data we have makes any difference to the outputs would be good to do. And then the sediment data within the channel, we know so little at the moment about exactly what those sediment characteristics are like and how they will evolve as the proglacial area is starved of sediment. Would be really good to start to investigate. And then the third area, of course, is what are the potential impacts? There are population data now increasingly available. Where are the local populations and how large are they? And in a future context, how large will they become? I suppose would be good to start to investigate. How vulnerable and exposed are people to floods? It's a big question, of course. But having more information on the socioeconomics would be good. And also, what are the infrastructure that can be impacted? And how does this change? Because some of these areas are so rapidly developed in the downstream now that actually this is something which constantly needs to be updated. And so some further challenges within that area to be able to get some answers to vulnerability with these ongoing events. So they're my thoughts really on what the key challenges are. We know still relatively little about the dam structures. The big uncertainties at the moment, not least in terms of the internal conditions and the presence or absence of an ice core. There's very high uncertainty, I think, in the location of future glacial lakes. We don't seem to have consistency between the different model outputs at the moment. And so thinking about how we handle that uncertainty to be able to still use those outputs effectively would be good. And then those questions that we just settled on in the previous slide are really long-standing questions which require a little bit more analysis of the downstream areas. This is something which is, of course, quite complex because there's a lot of variability from catchment to catchment. And as we said just at the end there, there's quite a lot of ongoing development in the downstream areas. So this is constantly evolving through time as well. So I'll leave it there and just say thank you very much for listening, and just say also thanks to some of my collaborators who you can see there noted at the bottom of the slide. Thank you very much.
Thank you, sir, for providing more context to how we can tackle these challenges, and it's encouraging to hear about the progress being made at different levels. Let's believe we as environmental scientists will surely grow and work even better into this area. Our next speaker is Professor Rijan B. Kayastha from Department of Environmental Science and Engineering, Kathmandu University, Nepal, a leading climate scientist specializing in glacier dynamics and GLOF modeling. With 30 years of experience as a glaciologist, we await to hear some useful insights into the topic. Over to you, sir.
Okay, thank you. Can you hear me?
Yes, sir, we can hear you.
Okay, good. Okay, so this is my slide. Can you see? Is it okay?
Yes, sir, we can see
Okay,
the
good.
slide.
Good. Sorry, I was interrupted in the beginning. Now it's okay. So I'm going to talk about the GLOF risks and resilience strategies for changing climate. And I would like to thank the SAIARD and the team and the SAIARD Himalayan Climate Consortium also. Okay, and I'm working as a professor at the Department of Environmental Science and Engineering, and also heading this Himalayan Crash for Climate and Disaster Research Center. So first, I will explain about a few terms which are very necessary to know about knowing this GLOF risk and resilience. Okay, crash. It includes all cold matters in the earth and its atmosphere: glaciers, sea ice, lake ice, river ice, snow, permafrost, and atmospheric ice. So these all include in cryosphere, and we have to know the glacier. I think the Professor Duncan has already mentioned that the glaciers are retreating. Therefore, we are having a larger and larger glacier lake. So this is an example of glacier. Glacier is a moving body of snow and ice that has been formed by recrystallization of snow. So this is an example of Rikasamba Glacier in Nepal, in West Nepal, Mustang district. And it was in October 2017. And this glacier has been studied since 1994. So we have a very good data set of this glacier, how it is changing. It is changing a lot. And the glacier lake, Professor Duncan has already shown many glacier lakes, and this glacier lake has also shown. This is the Lake Chorolpa. I was there in 1994, but this was taken in 1995. This is the lake. And the glacier lake is a lake formed by the glacier activity. Okay, so this is the Krakatau Glacier, Davis Covered Glacier. It was up to here in 1960s, 1958, 59, up to here. And when it receded, then we have this glacier lake. And on the glacier, so this is a Gozumba Glacier in Khumbu, and these small ponds we call as a supraglacial ponds, and when these supraglacial ponds enlarge and merge together, then we will have a big glacier lake. So this is small ponds on glacier and called as a supraglacial pond. Okay. And there are two types of glacier lakes. One is modern dam glacier lake like this, the upper one. So this is a glacier. Abrasion area is lower down, and above we have an accumulation area. So if we have a lake formed like this, bounded by the moraine, end moraine, lateral moraines, then this type of glacier lake we call as a moraine dammed glacier lake. And we have another glacier lake, which is called as a ice dammed glacier lake. Suppose if our glacier is up to here in the beginning, and if these glacier lakes are these streams are flowing like this, but it was interrupted when it advanced, it moves forward, then at the margins, at the end of at the lateral side of the glacier ice, we will have lakes, and those lakes are called as a ice dammed glacier lakes. So in the Himalayas, we have these two types of, mainly these two types of glacier lakes, but we have other types of glacier lake like in glacial lake also, inside the glacier lake also, inside the glacier also, we can have a big glacier lakes like in Iceland and so on. Now, so this is an example of modern dam glacier lake. And this is these two lake we can see here. These are the ice-dammed glacial lake. And now I will talk about the inventory of latest inventory work by Kathmandu University. And this work has been carried out by Rakesh Kayastha. He has recently completed this analysis, and we are going to publish this data very soon. So we studied 4 river basins, Koshi, Gandaki, Karnali, and Mahakali in Nepal. And those 4 river basins have glacial lakes in Nepal, China, and India also. Okay, so we have classified the glacial lake, glacier connected proglacial lakes, glacier fed lake, supraglacial lakes, which I have already shown on top of the glaciers, and non-glacier fed lakes like alpine lakes. And here we have considered the lakes only above 3,500 meter altitude, and total lakes from these different criteria, different categories. And in these 4 river basins, we found 4,254 glacial lakes. Okay, glacier connected 115, glacier fed 1,548, supraglacial lakes 1,045, and non-glacier fed alpine lakes 1,546. Altogether 4,254 lakes. And only in Nepal, we have total 2,372 glacial lakes, and largest number is this non-glacier fed lakes, 876. In these inventory works, we have considered the area of 1,600 square meter, means 40 meter by 40 meter lakes we have included here. And regarding that, this is also better to know that glacier are shrinking. So the 24% of the glacier area decreased from 1977 to 2010, and 29% of ice reserve decreased during this period in around 30 years. And these are the different subglaciarized river basins from east to west, Tamor, Arun, Koshi to Mahakali. So we have 19 subglacial river basins in Nepal, where we have glacier and glacial lake. All those glacial lakes are here. Means 2,000, that was 2,372 based on our recent data, based on the set images, set data of 2023. And so now I will talk about the recent, the GLOF events after 1980s that has caused damages in Nepal. So this is the list of 8 glacial lake outburst flood events that occurred in and outside Nepal that hampered or that damaged occurred inside Nepal. The first one is this Tamor, Nagmapuri, it is in Nepal. And second one is Potekoshi, that was in China, Tibet. And third one here, 4 August 1985, Dutkoshi, Dikcho glacial lake outburst flood occurred. And this glacial lake outburst flood is taken as an eye-opening GLOF event in Nepal, because only after this GLOF, the government of Nepal has started study on snow ice glacial lake. And then after 1985, we had a small glacial lake outburst flood in Tamakoshi River Basin. This is Chubung, we call that the Chubung glacial lake outburst flood event. It is very near to the Thorolpa big glacial lake of Nepal. And then Dutkoshi, Sabaicho, Potekoshi in Tibet again. And these two are again recent one, 2017. And this is the latest ones, which is already mentioned by Duncan also. So on 16th August 2024, in Thame area, we had the GLOF event. I will talk in details about that also. So this was the eye-opening GLOF event in Nepal, which occurred on 4 August 1985 and destroyed nearly completed Namche hydropower plant, 14 bridges, cultivated land, and caused many casualties in the downstream. So this was the lake, and huge block of ice fell from this glacier, Langmoche glacier, to this lake, and wave splash created, which was destroyed this Enmoren, and GLOF occurred in the downstream. And for example, so how the glacial lakes are enlarging or the development of different glacial lakes. So this is an example of Chodolpa Glacial Lake. There was only one big lake and four small ponds inside the glacier in 1957-59, and these small ponds merged and became one single large glacial lake in 1960-68, and then gradually it increased its area. Now its area is more than 1.89, I think. And so since we have many glacial lakes, 47 glacial lakes are very dangerous, potentially dangerous to Nepal. Out of 47, 21 are in Nepal, 25 are in Tibet, China, and one in India. So the government of Nepal has also carried out some mitigations activities like lowering the water level of glacial lakes, and that was carried out by Department of Hydrometeorology, Government of Nepal, with the help of UNDP fund as well as the third-party fund. So the Chodolpa Glacial Lake water level was lowered by 3 meters in 2000, and Imja Glacial Lake's water level was lowered by 3.4 meters in October 2016. So these two potentially dangerous glacial lakes water level has already lowered down. And this is the photograph of outlet of Chodolpa Glacial Lake in Dolakha district. So the reinforced spillway was built like this with a gate. Here we have a gate. And similarly, GLOF new outlet of Imja Glacial Lake here, that was completed in October 2016. So water is flowing like this from the lake now. And now I will talk about this Thame GLOF or the Tembo GLOF, Thame Sulkhumbu, which occurred in 2000. This year, August 16th. And the lake was here, and this lake was outbursted. And there are 5 small lakes. These are the 5 small lakes, and Dikjo is very near here. So in the next valley we have Dikjo, and on the right we can see, left here we can see Lumdingjo. So this is also one of the potentially dangerous glacial lake of Nepal. This is in one of that 21 potentially dangerous glacial lake. And so these were the 5 glacial lakes. So this is the uppermost one. 1, 2, 3, 4, 5 lakes are there in this Thame area, and the Thame village is down here, around 17 kilometers. I think 17 kilometers down we have a Thame village which was destroyed, and about 17 houses were fully destroyed, and others grounds, cultivated land was also destroyed, and there also partially damaged the one micro hydro power project. And this lake area, this lake was outbursted, and its area was 39,000 square meter. Okay, and the cause of this GLOF was outflow from this lake. Outflow from this upper lake, and that outflow drained nearly 80% of this lower lake's water. Therefore, there was a GLOF flash flood in the downstream. And the cause of this outflow from the upper lake was due to the heavy precipitation, heavy snowfall past few days, as well as high temperature thereafter. So it was melted out, and it overflowed this lake and came down, which nearly emptied the second lake. And down we had GLOF. And this was the lake which was drained on that 16th August. And the remaining water is denoted by this dark blue color. This much water, the other part has already emptied due to that lake. and about 0.3534 million cubic meter of water drained due to that GLOF event. And the possible causes of those of that TEMBO GLOF is the high melting of snow and ice due to increased air temperature, high precipitation before a few days of the event, and that was confirmed from Sangboche stations. Its altitude is 3,780 meter, and Force, which is also very near, 3,840 meter. 3,840 meters, yeah. And the overflow of the lake won and eroded the landscape down, causing a GLOF from the lake too. So these were the conclusions from the helicopter survey, as well as the interview from the local persons. And these are the proof that temperature also increased. Force maximum temperature at Force increase on this August 13th, 14th, increase temperature a lot. And then the precipitation also very high on August 14th. So precipitation also Sangboche rainfall. This is Sangboche, and this is Force. In both high altitude areas, it was increased, and maybe in that area, because we don't have weather stations in the Thami area, so we can't say exactly how much precipitation was there, but surrounding stations showed that there was a high precipitation 2-3 days before. And now what we are doing, so we have also like before that Professor Duncan has also mentioned that how to know the strength of the moraine dams, and if GLOF occurred, what will be the downstream, how the flood water will propagate in the downstream. So we also done this GLOF modeling using a simple Hecras and dam bridge model. This paper we have already completed and submitted to a journal. It will publish this soon, I think. So this is the Sorolpa Glacial Lake again, and it is flowing like this. This is the location of in the map of Nepal. So we have carried out this GLOF modeling work in order to know what will happen in 20, 30, up to 40 years from now, from 2020 to 2021 to 40 years after, how it will grows, and if GLOF occurred after 40 years, then how its water will propagate in the downstream. So this is the research design. We have used the glacial lake and surrounding informations, bridge parameters. We use the Hecras and flood routing. So for the bridge, we have used this NWS bridge modeling, and frolic peak flow relations was used. And then, so we have estimated what will be the maximum discharge in 40 meter, around 26 thousands meter cube per second, and in case of 20 meter bridge, it's around 9,000 meter cube per second. And these were the flood height in the downstreams from the glacial lake to 190 kilometer downstream. So there were two peaks in case of this 40 meter bridge. Here around the 50 meter, and then around in 185 meter, the peak will be there. The flood height will be the maximum in those two events. And this is the location map of Sorolpa, and we have carried out this Hecras in order to know how the flood water will propagate and where it will ponding, or what will be its maximum depth, flood depth. So flood depth will be maximum around here, and here we have another this. So this is the Tamakoshi River from Sorolpa, and this is the Sunkoshi River. Okay. And maximum depth we found here, and we also checked that whether once it outbursted by 40 meter, whether this water will reach to Nepal-India border or not. We found that this will not reach up to there. It will be inside the Nepal, and about how many kilometers? It's around 40 kilometers from the, this there is another Potekoshi River from Dutkoshi River Basin. So it will go a little down from that confluence point. And in the Dutkoshi also, we have 9 potentially dangerous glacial lakes. So if this Chorulpa, GLOF, and those lakes, one or two in Dutkoshi River basins, if simultaneously occurred, then it will be actually damage will be very high. But if single GLOF occurs, the damage will be less here, because these are not so inhabited. The local peoples are not much in these floodplain areas. Only we have it down, but in the down, its water levels as well as the flood volume will be less once it travel more than 100 kilometers down. And so these were the maximum discharges we have calculated. What will happen after 40 years if this lake burst after 40 years? Because we have considered linear expansion of the lake from present to 40 years now. So in 40 years, its discharge was more than, this is 12, no, it's 11,000, around 11,000 meter cube per second will be the maximum, and it occurred around 7 hours from its bridge. And so not only in Nepal's, I think Professor Duncan has also mentioned that we have many glacial lakes, and there are already many GLOF events in the recent past. So Sikkim GLOF, he has also mentioned this was occurred on 3rd October 2023, and this is the location map. So the South Lonak Glacier is here, and when it bursted, then so this was the South Lonak Glacier. This was in 2016, maybe already here, and it was outbursted. Due to that, we had like this destruction. So the this Lonak lake in the North Sikkim decreased, causing massive devastations, and 1,200 megawatt Tista Thorder dam downstream was destroyed, resulting in 40 lives lost, 76 still missing, and intensive damage to infrastructure like these. So not only in Nepal, we have such big glacial lakes all over this Himalayas, as well as in Karakoram also. And this was the Chamoli flood in Uttarakhand in India in 2021, 7th February. So this was not a glacial lake flood, because we don't have big glacial lake or the small glacial lake like that Klame GLOF in the Chamoli area, but there was a heavy rain, snowfall in the previous few days to the few weeks, and thereafter the temperature increased a lot. So the glacier, so it is not a glacial lake outburst, but the glacier outburst were due to heavy snowfall in the higher reaches in the Rishi-Ganga catchments, followed by heavy frost, means melting. The snow became hard and got glacier shape immediately after the temperature increase and moisture decrease, which led to the glacier outburst. And once the snow melted out, a huge amount of meltwater rushed down, and those rush water also brought the debris on its way. Then this is Kedarnath flood in 2013. This is also not a glacial lake outburst flood, but it's a debris flow and flash flood due to heavy precipitation, and it was overtopped the pro-glacial lake of this glacier there. And then in the downstream, it was a devastation like this. So Rudraprayag is here. So the Kedarnath is located here in the Rudraprayag district, and this was the destructions at the time. More than 10,000 people were lost by the debris and many animals together. So now, at the end, after knowing these things, what do we have to do? What we should do strategically so that we can minimize the GLOF events, as well as to minimize, if even GLOF event occurs, to reduce the physical as well as the infrastructure damages and human casualties. So we need to monitor glacier and glacial lakes and prepare, update inventories in every 5 years. Need to install more weather stations with snow depths sensor at high altitude so that we will be known what is happening at the high altitude. So in this Thame GLOF recently, also we didn't know how much precipitation was there. And in Somali also there was a huge snowfall in the past few days, a few weeks. So those information, if we have, then we can take a precautionary measures. Need to install GLOF and flood early warning systems. So in the downstream of those glacial lakes and small lakes areas or the glaciarized river basins, we need to install glacial lake outburst flood or the flood early warning system by installing this automatic water level sensors in the downstream riverside. Okay, and there should be the proper communication facility also, so that we will get timely the information. Need to make mandatory to install weather and hydrological stations and cryospheric studies once the high mountain hydropower license is issued in such Himalayan countries. I think in Nepal also we are saying that they must install early warning system as well as the weather and snow depth sensor station with stations and high Himalayas, so that we will get the proper information, so that we can warn the peoples in the downstream. And locals should also be abide, or they have to obey by the river corridor rules for building construction, because in most of the river areas we have some rules and regulations that they can't build the houses or any other buildings very near to the river banks. It depends on how big the river. We have different 20-meter, 30-meter, 40-meter areas should be vacated. Only after that 20-meter or 30 meters, they can build the houses and others. So those rules should also be followed by the locals, so that even if the flood or this GLOF occurred, then the devastations or the casualties will be very less. So I think we should recommend such strategies in order to reduce the GLOF events or any other flash flood events in future in those glacier river basins. With this, I would like to conclude. Thank you very much for listening and watching. Thank you very much.
Thank you, Professor Rajanbi Kayastha, for those insightful findings, and your recommendations would surely be looked into in the future. It is clear that science is playing a pivotal role in helping us understand the evolving nature of these risks. Now, at this point, I would like to open the floor for any questions or comments from our audience. Please feel free to share your thoughts and we will direct them to the appropriate speaker. If you have any questions, you can raise your hands. Well, I say there are no questions. I hope today's discussion was enriching to everyone with new perspectives and strategies that we can take back to our organizations and regions. Together, we can help reduce the risk of GLOFs and build a more resilient and sustainable future for all. Okay, there's a question now. So, Shivang Alok, you may ask the question.
Good afternoon, sir. Sir, there is a one question. Means both of you can, if give it answer. Is there any method that we can get to understand the dam stability based on remote sensing data? Because it is not feasible to be collect data, ground data for Himalayan glaciers. So, is there any method that we can get the dam stability data from any source?
Thanks, Shivang. I think it's tricky. You know, the remote sensing data, as you know, tells us what's going on from the surface. We can get some indication of whether there's a degrading ice core by using digital elevation models. And I think the ice core degradation is probably one of those parameters which is going to give a good clue as to the stability of a dam or otherwise. But even then, it's difficult to say, well, if there's this rate of degradation for the ice core, what that means in terms of stability. So then I think you have to go into some sort of basic numerical modeling, which is what we've been doing with Slope W. And I'm pretty sure that you can get that kind of software on a student license and maybe even open source. I don't exactly know what would be most appropriate for you, but then to put in some material parameters isn't actually that difficult, and to do some sensitivity is not that difficult either. So I think the answer to your question, it's a bit of a longer answer, sorry, but I think the answer to your question is probably not just from remote sensing by itself, but by combining those sorts of observations with some basic numerical modeling. I think you can start to get some indication. The tricky part then is to know, well, actually, what happens if a big displacement wave comes along? Because as Rijan's talk quite nicely pointed out, there tends to be a trigger for these things. They don't just tend to collapse, which is what the slope stability analysis will give you, is will it just collapse? But actually, in reality, these things very rarely just collapse. There is also a trigger event, like Rijan was talking about, and trying to model that is actually quite tricky.
Yeah, I also agree, Duncan, that we can't get all information only from using the satellite data. And in satellite data also, if we have, it should be very high resolutions, 1 meter, a few centimeter, 50 centimeter. Only then we can analyze how the moraine is degrading, or if there is ice, how that ice core is degrading by using the very high resolution satellite images. Otherwise, it will be very difficult. Yes.
Thank you, sir. Thank you.
Yeah, okay, sure.
Thank you, both of you, for answering the questions. And I hope that Shivang's queries are being satisfied. I hope today's session was enriching. And thank you for attending. And I wish you all the best in your ongoing efforts to address these critical challenges. Let's hope with more findings, we would have another meet and share our works into this field of glaciology. Thank you very much. With this, let's complete our session.
Thanks, Amrita.
Okay,
Bye for now.
thank you, Duncan.
Cheers, Rijan.
Okay, good.